Alright, so in the last video we set the foundation, if you like. We set the premise, which was a simply supported beam. We identified a specific position within that beam, and we used some fairly familiar methods, some familiar equations to determine the stress, the normal stress due to bending, and the shear stress that would occur on a cut that was made vertically down through the beam. So the goal now in this lecture is to determine what are called transformation equations. And very simply, our objective here is to determine a set of equations that will allow us to determine the normal stress and the shear stress that develop at a point on a plane at some other orientation theta. So previously we looked at the stresses developed when theta was 0, i.e. the stresses developed on a vertical plane. Now we're going to determine these transformation equations, which give us sigma, the normal stress, and the shear stress tau as a function of theta, as that angle changes. Really all this means is, if you want to tie this back to sort of a practical case, you know, how do we relate what I'm talking about now back to our beam? All we're saying here is let's imagine that same beam, right? I won't draw the beam again, but let's just the full beam. Let's imagine instead of taking a vertical cut, now we took a cut at some angle. So now this is our cut surface. This is our cut surface. An outward pointing normal from that cut surface perpendicular to the surface would be like this. Our horizontal x-axis would remain like so. And now the big question is, if I know theta, can I work out the normal stress that develops on this face, this inclined face, and the shear stress that develops on this inclined face? That's what this lecture is all about. All right, so let's start off by just making a couple of statements here. We're going to first of all talk briefly about this concept of plane stress, okay? Because everything we're going to look at now is going to be based on a condition of plane stress. We're assuming our beam here is in a state of plane stress. So previously, we're just going to call this a refinement. Okay, a refinement of our problem. We're essentially defining an assumption here, okay? And what we're actually doing is, which is what we do quite commonly in engineering, and certainly when we're deriving things, we're going to reduce the problem. We're going to reduce the problem to a slightly easier to manage thing. So in the last video, we said we had a stress element. We had some stress element, which was an infinitesimally small element, right? You can think about it as a tiny, tiny element. And we had a set of stresses. I'll just arbitrarily draw on some stresses here. So this is going to be sigma x, because it is a normal stress that is acting on the face where the outward pointing normal points along the x-axis. So I should draw on an x-axis then. So that's my x-axis and that's my y-axis. And because the stress sigma x acts along the same direction as the x-axis, we call it sigma sub x. Similarly, this guy is going to be sigma sub y. Same for this guy, sigma sub y, and then this one obviously is going to be sigma sub x because it points in the negative x-axis direction. Then we're going to have our shear stresses. Let's just draw some arbitrary shear stresses on here. I'll draw that guy there. Now he is going to be tau sub xy because he's acting on the x face in the y direction. Okay, the x face, because again the outward pointing normal for that face is along the x-axis, and it's acting in a y direction because the direction of the arrow is along the y-axis, so it's tau xy. Then we've got this guy here will be tau yx, y face x direction, and let me see, this one here is going to be again tau y face x direction, and this one's going to be tau x face y direction. So tau xy, tau yx. Okay, so that's how we're denoting our stresses. Now, we said that was a 2D picture of what is actually a 3D stress element. So in reality, our stress element is going to be something like this. And so we're actually going to have an x-axis, we're going to have a y-axis, and we'll have a z-axis, which we can think of as pointing out of the page, right? And so if we were doing a full 3D analysis here, we would potentially have a stress in that that z-axis direction, a normal stress, and we call that guy sigma z, and we could have a sigma z behind it here. Let's just call that sigma z, and we could have shear stresses acting on that z face as well. Let's just call that tau z face y direction, and you know we could have a shear stress on the back here, and well, we might as well complete the picture because we're going to have again complementary shear stresses. We would have a shear stress developing on the top face here. We would call that tau yz, and we'd have a shear stress. It's getting messy now, but that would be tau yz on the bottom face. Right, all I'm trying to say here is that there is a whole set of stresses that could potentially exist on our 3D element that we are not representing or showing on this 2D element. Now, why are we doing that, and how can we do that? Well, for very, very many structures, for a lot of structures, it's perfectly acceptable to completely ignore these stresses that develop on the Z face. Not in all cases, but in many cases, because the magnitudes of those stresses that develop on those Z faces are going to be so much smaller than the magnitudes of stresses that develop on the X and Y faces, which is what we're seeing over here. So what we're saying here, common simplification, what we're saying here is if sigma Z, if it's close to 0, or if it's very, very, very much smaller than the magnitudes of stresses on the X and Y faces, and if tau zy, which we know is equal to tau yz, if they are approximately equal to 0, or again much smaller than the stresses that develop on the other X and Y faces, well then, okay, the stresses on the Z face are very small or 0 compared to those other stresses, and so we can ignore them. Okay, they're very small compared to stresses on the X and Y faces. This is a condition we call plane stress. It's a condition, it's an approximation, right? It's just an approximation. So we're taking a 3D element and we're simplifying it down to a plane element, a planar element, with stresses only existing on the X, in this case, the X and Y faces. So this is a simplification called plane stress, and again, it's a very common condition, a very, very common condition, and so that's why we often start out simplifying our analysis down to plane stress. So now that we've dealt with that, we can move on, and we're going to the next thing we have to sort of nail down here is a sign convention for these stresses. So we'll start off with the easy one. So the sign convention for normal stresses is very easy. In fact, you almost certainly know this already. So the sign convention is compressive stresses are going to be negative and tensile stresses are positive. Tension is going to be denoted by arrows that are pointing away from the surface, okay? So trying to stretch or pull the element, tension the element. So compression is going to be denoted by arrows that are compressing, squashing, pointing towards the face, okay? So that's nice and easy. For shear stresses, it gets a little bit more involved. So for shear stresses, I'm going to write the sign convention first, and then I'm going to tease it out and explain the different parts of it. So it might not make much sense for the next minute or so, but then it'll start to become clear. So for shear stresses, I've got to first of all determine or define a shear direction. Let's call it the shear arrow, okay? Again, bear with me here if this is new to you. Then we're going to define the face, right, whether it's a positive or negative face, and the result of those two pieces of data for a given face will determine whether the shear is a positive or negative shear. Sign of shear. Now, I could have a positive or negative arrow direction, right? So I could have a positive here, or I could have a negative, right? Now I can have a positive or negative face as well, right? So I could have I could have four combinations here. I could have a positive face and positive arrow direction, so positive and positive. I could have a negative arrow direction and a negative face. I could have a positive and a negative, and I could have a negative and a positive. Right, okay. These are all the different combinations I could have. Now, this is where it gets a bit easier. A positive arrow direction acting on a positive face will give me a positive shear. Okay, that is a positive shear. A negative arrow direction acting on a negative face, negative times a negative, would also give me a positive. A positive times a negative would give me a negative, and a negative times a positive would give me a negative. So these really are just, once you know what this is, and once you know how to define these two things, these are just the rules of multiplication to determine the magnet or the sign of the stress. So let's think about what is a positive face and what is a negative face. Positive faces are positive if the outward pointing normal for that face, let me just draw on my X and Y axis. The outward pointing normal for the face is acting in the positive axis direction, it's a positive face. Think about this right hand face, vertical face. The outward pointing normal points in that direction in the same, so it's pointing in the positive x-axis, and therefore this red here is going to be a positive face. Similarly, the outward pointing normal for the top face is pointing along the positive y-axis, and so that's going to be a positive face. Think about this outward pointing normal for the bottom face, points in the negative y direction. I should have called that y. This points in the negative y direction, so the green bottom face here is going to be a negative face. This guy is pointing in the negative x direction, and so this face, i.e. the outward pointing normal, is pointing in the negative x direction, and so that's a negative face. That deals with this guy. We've understood how to define a positive and a negative face. Now we've got to think about the arrow direction. Right, now the arrow is deemed positive if it's pointing in a positive axis direction. So imagine an arrow on the right hand face here. If the arrow pointed up, right, that would be a positive direction arrow because it's pointing in the positive y-axis, same direction as the positive y-axis. This arrow is a positive arrow because it's pointing in the positive x-axis. Okay, if I flipped those arrows around, they would be pointing in the negative direction of the respective axes, and they would be therefore defined a negative arrow. Let's define some negative direction arrows. Let's look at this guy. This arrow is pointing in the negative x direction, so it's a negative arrow. This arrow is pointing in the negative y direction, so it's a negative arrow. So we'll call those negative. Now, by combining those pieces of information, I can define positive shears and negative shears, right? So if I think about positive shears to start off, if I think about what a positive shear would be on the right vertical face, well, that is a positive face. If it's a positive face, right, I'm going to need a positive shear direction, right? Because I've got a positive face, right? The only way I can get a positive shear, let's say I want to define positive shears here. The only way I can get a positive shear on a positive face is by applying an arrow in the positive direction. So that means that is defined as a positive shear on that face. Now, because of the rules of complementary shear stresses, if I know the direction of the shear arrow on that face, well then I know it must go that way on that face, it must go that way down here, and it must go that way over there. These are positive shear stress. Positive shear stress. And you can confirm that by looking at any of the other faces. Let's look at the left-hand vertical face. Okay, left-hand vertical face, it is a negative face. All right, it's a negative face. So that would mean that guy there. Now, it's also acting in the negative. The arrow is pointing in the negative y direction. So that's going to be a negative there. And of course, that's going to give me my positive. Okay, so all of those shear arrows on those respective faces are positive shear stress. Now we can do the same thing just to confirm. Let's draw on the negative case. So now, if I think about my right-hand vertical face, now if I'm defining negative shear stress, well, that's actually a positive face, that right-hand vertical face. And so to get a negative shear stress there, the arrow must point in the negative axis direction, which is going to be downwards. And of course, that defines the direction of all of the other arrows. So that means that one goes there, that one goes there, and that one goes there. So all of those guys are negative shear stresses. So that is our sign convention for shear, right? It's determined by the sign of the face, whether it's a positive face or a negative face, and then by the direction of the arrow on that face. And we use the rules of multiplication in order to determine the sign of the actual shear stress itself, whether it's a positive shear or a negative shear. The next thing now that we're going to do is actually derive these transformation equations. So that's going to be the next step. So let's start off with a 2D element with some stresses on it. So this is my starting state of stress, and let's make the assumption I know this, right? So the question is, let's just say if I know this, all right, in other words, if I know what all of those stresses are, the magnitudes of those stresses, can I work out the stresses on an element orientated at some angle theta? So let's just sketch that. Okay, so if I know the stress state on the left-hand side, the question becomes, can I determine this? Presume I know theta. Can I determine, if I know theta, can I determine sigma x1, sigma y1, and tau x1, y1? All right, and that's, well, the answer is yes. And we're going to do it, you use transformation equations, and that's what we're going to derive now. So we're going to start off, the classic way that this derivation starts off is by considering a wedge element. So we can imagine an element which has a vertical face, right? It's got a horizontal face, but then it also has an inclined face. And of course, there's going to be stresses that develop on these faces as well. Okay, so the interesting thing here is because we have an inclined face, I'm going to draw it in red here, but we've got a stress normal to that face, which we're calling sigma x1, and we have a stress parallel, and the stress parallel is obviously a shear stress being parallel, which is going to be tau x1 y1. So this is the starting point, because this element here gives us a bridge, gives us one element that has the stresses from both different conditions, both different orientations acting on it. Okay, so that's why it's a nice little element to start off this derivation. So we're going to start off and we're going to say that the area of the negative x face, okay, the area of the negative x face is going to be a0. That means, therefore, the area of the y face, is going to be, let me see, a0 times the tan of theta, the angle theta, and then the area of the inclined face, just simple geometry of a right angle triangle going on here. Let's call that the x1 face, right? The x1 face, well, that's going to be a0 over the cosine of theta, and 1 over the cosine is equal to the secant, right? So that's going to be a0 times the secant of theta. All right then, if I take all of those stresses and I multiply them by the areas that I'm just after working out, right? So this guy, and this guy, the relevant area multiplied by the relevant stress on that face, we're going to get forces, right? So I can actually work out a free body diagram. I can sketch a free body diagram of this element. So we'll say a free body diagram of our element, which is just obtained by taking the force being equal to the stress times the area over which that stress acts. Okay. All right then. So we've taken our wedge element, multiplied stresses by areas, and we've ended up with a free body diagram. The element is in a state of static equilibrium, and so we know the sum of the forces acting on this element must equal 0. Okay. That means that we can consider the forces, the sum of the forces along two different orthogonal directions, and each one must be equal to 0. So what we're going to do is we're going to first of all consider the sum of the forces in the x1 direction, right? The x1 direction was this direction here, which was along the x1 axis. Then we're going to consider the forces along the orthogonal direction, right? Which obviously is going to be the y1 direction. That was your one direction. And so out of those two force equilibrium equations are going to drop our transformation equations. Now things are going to get a little bit hairy here when it comes to deriving these equations, only because they end up being kind of long and tedious with a lot of different elements and symbols within them, but there's nothing complex going on here. It's just a force equilibrium equation. Let's start off by taking the sum of the forces in the x1 direction. We know it must equal 0, and we're going to assume forces in the positive x1 direction are positive. All right then, so this gets, as I say, it gets a little bit tedious. It helps if you break these down, into their components to help visualize them, right? So let's think about the components of this force on the vertical face, the left vertical face here. Well, that could be broken up into a component parallel to the x1 direction and perpendicular to the x1 direction, where that is my angle theta. Similarly, this shear force on the horizontal face could be broken up into a component parallel and a component perpendicular to the x1 direction, where that is theta. And we can do the same thing, only use red this time. So we can break out the normal force on the negative x face like so. And what else have we got? We've got this guy. So he breaks down into that and that, where that's theta in there. All right, so we're breaking these components, these forces down into their components in convenient directions, and now we're just going to consider the sum of the forces. Obviously, this guy acts in the positive x1 direction, so we'll start off with him. So we'll say sigma x1 times a0 times the secant of theta. Let me see, right, everything else is in the negative direction, right? So we've got sigma x, so I'm dealing now with this, no, we shouldn't do that, with this component here, right, that guy there. So that's going to be sigma x times a0 times the cosine of theta. So I'm going to just make this very obvious. I'm going to draw a line between him and him. There, okay. All right, so that's the sum of the forces in that x1 direction. Now, thankfully, all of that simplifies down fairly quickly and fairly easily. It simplifies down to the following. We're going to rejig that a little bit in the next lecture to get it into a more familiar form. But so far, for now, we're going to call that A. And what is it? That is a transformation equation, right? Because that gives us the thing we're looking for, sigma x1 as a function of sigma x, sigma y, tau xy, and theta, right? The things that we know. So to get the second transformation equation, to get tau x1, y1, the shear stress on that inclined plane, we're going to consider the sum of the forces in the y1 direction equal to 0, and then we'll say forces in the positive y1 direction are positive, and we'll do the same thing again. Now I won't be as I won't start drawing lines all over the place, otherwise this will get very, very awkward. But essentially we're doing the exact same thing that we've just done for the x1 direction. So let me jot out these force components. So now we can tidy all that up a little bit. And ultimately, when we do our tidying up, we can rearrange that. Again, nothing too complicated going on, just a little bit of tidying up. We end up with tau x1, y1 equal to, excellent, let's box that guy up and call that B. So A and B are our two transformation equations, right? Because in this case, the one we've just worked out, that gives us the shear stress on that inclined plane as a function of the normal stresses, right? Or the stresses on the horizontal and the vertical plane, and the shear stress on the same horizontal and vertical plane, and theta. Okay, so what have we got so far? Remember to keep in mind, despite the fact that all this gets very, I'd say ugly looking, complicated looking, it's still fundamentally a simple thing we're trying to do. We're trying to relate, we're trying to say, if I know this state of stress, and if I know my angle theta that I'm changing my orientation to, what are these stresses? And I have derived here fairly simply two equations that are going to give me that. So in simple terms, I've worked out sigma x1 as some function of sigma x, sigma y, tau xy, and theta, and I've worked out tau x1, y1 as a function of sigma x, sigma y, again tau xy, and theta. All right, which is at the simplest level, that's all we're trying to do, right? Work out transformation equations. Well, we have them. There's a lot more though that we can derive out of, or there's a lot more understanding that we can drag from these equations. When we start using Mohr circle to visualize these equations, we're gonna be able to understand an awful lot more, and a lot of key information about the state of stress at a particular point in the structure. So I think I've said enough for now. We've a lot of the hard work done, a lot of the really awkward number crunching done. We're going to come back, or not so much number crunching as symbol crunching. We're going to come back in the next video and we're going to jump into a little bit of Python, and we're going to start plotting these equations and starting to tease them apart and try and understand them a little bit more, try and dig out what it is they're telling us. So as I say, take a break, we'll come back and pick it up with a little bit of Python in the next video.